Alright, welcome back. So in this video, I'll be doing day 12 of the 30 Days of ML Challenge by Kaggle. And so if we look at the schedule, day 12, we're doing 3 lessons within the Intermediate ML microcourse. Lesson number 1 is called Introduction, lesson number 2, Missing Values, and lesson number 3, Categorical Variables. Alright, without further ado, let's have a look at the Intermediate Machine Learning microcourse. So in this video, we'll be covering lesson number 1, lesson number 2, and lesson number 3. All right, let's have a look at lesson number 1, Introduction. So Intermediate ML is directly follow-on. It's a direct follow-on from the previous microcourse, which is called Introduction to Machine Learning. And if you haven't already watched my past couple of videos, I highly encourage that you go watch those videos first, because in those videos and in that particular course, we built the foundation, the foundational knowledge and understanding that we need in order to complete intermediate machine learning. All right, so let's have a look. So here we are introduced to a couple of concepts that we'll be covering in the intermediate machine learning microcourse. So here we are looking at missing values and categorical variables, which is this particular video. And the next couple of videos, we'll be looking at designing pipelines, cross-validation, gradient boosting, as well as leakage. And here is just, I guess, speaking about the house prices prediction competition that we spoke about in the previous video. And some prerequisites, which is exactly like what I just told you guys. So if you haven't already watched the Introduction to Machine Learning course just yet, make sure you complete that course first, or at least watch the past couple of videos that I put out, which goes through topics like model validation, the concept of underfitting and overfitting, as well as random forests. So yeah, so we're starting off nice and simple. I guess this is just a recap as well as an overview of what to expect in the next couple of lessons. So let's move on to our very first exercise. All right, cool. So let's just run this first cell. This first cell, as usual, is for setting up our notebook. And in this video, we are looking at the house price prediction competition, which contains the house prices in the state of Iowa in the US, containing 79 explanatory variables, also known as features, and we want to predict the final house prices for those houses. All right, cool. I guess all of these are pretty familiar, so we want to read in. First of all, we import pandas, which is a library for data wrangling, data manipulation, and next we want to import train test split. Next we have xfull, which is where we'll read in the training set, and then we have an xtestfull, which is reading in the test file. And these are the features that we want to include in our model. So we have 1, 2, 3, 4, 5, 6, 7 features that we want to include. And then we want to train test split. We want to split the features as well as the target into these 4 variables. So we have the features for the training set, we have the features for the validation set, we have the target for the training set, we have the target for the validation set. And we are setting the train size to be 0.8. So that's pretty much it. So let's just go ahead and run this cell to set up. Everything's already done for us. Cool. And x.head just shows us the first 5 rows of our training data. Cool. So here's the first 5 rows, and across the columns we have the features that we want to include. So here we have 1, 2, 3, 4, 5, 6, 7 features that we just looked at from early on. So we have lot area, the year, how the house was built, the first floor, I guess this is square footage, I think, second floor, full bathroom, bedroom, and total rooms, I'm not sure. Total rooms above ground, I believe that's what it means. Cool. Next we want to import random forest regressor, which is a machine learning model that helps us predict the house prices in this particular scenario. And so here we are defining 5 models. Well, they're all random forest regressors, but the difference is they have different parameters. And then we want to, what are we doing here? So we're defining a function called score model, which takes in the model that we want to use along with our 4 data. So we have x train, x valid, y train, and y valid. And what this function will do is it'll fit the model to the training set, and then it'll predict the features on the test set, and then it'll calculate and it'll return the mean absolute error between the predictions, preds, as well as the target in the test set. And then yeah, we just want to return the mean absolute error. And then I think this one just prints out. So it's going to loop through all the models. So we have 5 models. It's going to loop through every single model and just print out the corresponding mean absolute error. So let's have a look. Cool. So it's slowly printing. Cool. So here, so these are our 5 mean absolute errors for our 5 models. So as you can see here, which model performed the best. So I guess this one, model number 3, so 23.5 thousand. Because so the reason why this model performed the best is because it has the lowest mean absolute error. All right, cool. So the best model is, as we said, the model that has the least or the lowest number for mean absolute error, which in this case is model number 3. So we're just going to go ahead and type model 3 and check our answer. Correct. Step 2, we want to generate test predictions. So my model is, so now that we know model number 3 is our best model, we want to go ahead and define it. So let me just go up and define model 3. Model number 3, I think this should be correct. Nothing too crazy so far. Run the next code cell without changes. The code fits the model to the training and validation data and generates test predictions that are saved into a CSV file. Cool. So this is just going to fit to the data, predict X tests, and then put our output into a pandas data frame. And then we want to save that data frame into a CSV file. All right, that's pretty much it. So we don't have to change anything. Cool. And then, yeah, I probably won't go through all this. This is pretty straightforward. So this is going to bring you, so if you hit on this link here, this is going to bring you to the competition page. And on there, you can join competition, which I think I've already covered all of this in my previous video. So yeah, just follow all of these steps here. Submit the data frame, the CSV file that you've saved, and then it'll return your performance or your results for your predictions. All right, yeah, I'm gonna skip that. You can do that in your own time. With that said, let's move on to lesson number 2, which is missing values. All right, cool. So I think we briefly talked about missing values, did we? I might be wrong. We briefly discussed the concept of missing values in our previous course, which is the Introduction to Machine Learning course. So missing values is, as the name suggests, is missing cells in our data frame that don't have values. And there are many ways that we can end up with missing values. So here we have 2 reasons why a missing value might exist in a particular data frame. So here, for example, if you have a feature that is used to describe the size of a 3rd bedroom, if a house only has 2 bedrooms, that means it won't have a 3rd bedroom. Or it could be just that the survey respondent hasn't choose to disclose or provide information for a particular feature. So here, for example, the example that they gave is that a particular survey respondent may choose not to disclose its income. So for example, if we have an income column in our data frame, and if that person does not choose to disclose his or her income, we'll have a missing value there. So here we introduced the 3 approaches that we can deal with missing values. The first one is simply just dropping the column that contains missing values. So here, for example, we have 2 features called bed and bath. We have a missing value here in the bed column, and we just drop that column entirely. Now, this is probably not the best way to go about it, as they discuss in the description here. And the reason is because we don't want to simply compromise or get rid of a feature just because it has 1 missing value. What if that feature is like really, really good, or really has really high predictive power, and just because we have 1 missing value, it's not worth it to just drop the entire column or the entire feature completely. Option number 2, which is imputation. I wrote an article on the concept of imputation, now how we can do that in scikit-learn. I'll put a link in the video description. So essentially what imputation is, rather than dropping a row or a column, imputation involves filling those missing values. So for example, we can fill a numerical variable, a missing value in a numerical column with the average. We can also fill it with the median. If it's a categorical variable, we can fill it with the mode, which is the most frequent value. So let's have a look here. So here we are imputing this missing value in the bed feature with the mean. So if we calculate the mean of the bed column, so we have 1 plus 2 plus 3, which is 6. 6 divided by 3 is 2, which is the mean, and then we want to fill that missing value with the value of 2. All right, method number 3 is called an extension to imputation. So what are they doing here? So here they're creating a new feature called bed was missing, and essentially this feature is just a flag of the bed column. So if it has, if there's a missing value in the bed column, we want to flag in the bed was missing column that that row is missing. If it is not missing, we just want to flag it as false. That's pretty much it. Now let's look at some concrete examples just to reinforce our understanding. So let's have a look at the show hidden code here. So I think all of this is pretty familiar at this stage. If you've been following for the past couple of videos, this is pretty straightforward. So we want to import the libraries, we want to load the data, we want to get the target, and we want to get the predictors. So these are all our features. We are saving it into this particular variable. And then we want to do train test split, which divides our training and validation data. So let's go ahead and close this. And then we want to define a function to measure the mean absolute error. So this is what the function is trying to do. It'll take in our data sets. We want to instantiate the model, fit the model, and then predict, and then return the mean absolute error. Cool. So here we're just applying we are applying the function to the 3 approaches and comparing the results and see how they perform individually. So here you can go through all of this. It's pretty straightforward, I think. So the mean absolute error, so the final result that we get from all of this is 183,000. This is the mean absolute error from approach number 1, which is we drop the entire column, which is not ideal. So we probably would expect this would have a higher MAE than the next 2 approaches. But let's just move on and see if that's the case. Approach number 2, imputation. And the MAE for imputation is 178,000, which is less than 183,000, which proves that approach 2 is better than approach 1. So let's look at the final approach, an extension to imputation, and see how it performs. So the MAE for approach 3 is 178,000. So approach 3 performs slightly worse than approach 2. So I think out of all 3, approach 2 is the best. So they pose a question saying that why imputation performs better. And that is because exactly like just what I just explained from a couple minutes ago. So if you drop a column, you might run into the risk of removing a lot of useful feature, and we don't want to risk just because we have a missing value in the column, we drop the entire column completely. We want to either impute them or just drop a single row. We don't want to risk an entire column or feature, especially if we think that they're a feature that has a very high predictive power. So you can also have a look at the number of missing values in a column. And the way you do that is via this dot method. So here we're actually doing 2 dot methods. So first we want to do isNull. So isNull is going to return true and false if a row is missing. And then once we do that, we want to do dot sum. So we want to sum up all the number of missing values. So that's going to return the number of missing values for each feature. So for example, here we have 3 features that have missing values, 1, 2, 3, and these are the corresponding missing values in those columns. All right, that's pretty much it. So I guess in conclusion, just to summarize, in this lesson, we looked at 3 main approaches. Because approach 3 is an extension from approach 2. So approach 1 is if we have missing value in a column or a row, we can just drop those missing values from the data set. But in doing so, we have to be mindful that we don't want to drop, we don't want to lose too many useful information in the process. Approach 2, which is a better approach, is if we impute, which is filling those missing values with a replacement or with a substitute value. So just to go back on the article that I wrote, within imputation as well, the different ways you can impute. What we just looked at in the example earlier on is what is called a univariate approach in imputation, which is we're considering just one column by itself. We're just taking the average of that one single column. There's also something called a bivariate or multivariate approach to imputation, which is we consider the other variables in the data set when we're doing imputation, which is even better than a univariate imputation. I'll put a link in the video description, my article that I wrote on this particular topic. The last but not least, approach number 3, which is an extension of approach number 2, which is we create a new column, which acts as a flag whether or not a missing value exists in a particular column. I hope that makes sense. So let's move on to the exercise. We are back. So let's run this first cell for setting up. I think we're using the same data set again. So it's the house prices in IOR data set. All right, cool. So I think it's finished. Yep, setting up. So cell number 2 is just basic, I guess, reading the data set, splitting into training and validation set. And then we want to look at the first 5 rows of the data set, of the training data. So this is our training data. So we have a lot of features here. You can already see a few missing values in the first few rows. In the next step, you'll attain a more comprehensive understanding of missing values. So let's have a look at the missing values. So here we have 1. In the lot frontage column, we have a missing value. What else? Yeah, I think that's the only one. I'm sure like there's some missing values here in the column as well. They just do ... because we have too many features and pandas doesn't display everything. Yeah, so we have 36 columns altogether and we're looking at the first 5 rows. All right, so let's have a look at the shape. So dot shape shows you the number of rows and the number of columns. And then we want to do isNull.sum, which I talked about when we were going through the lesson. And then we also want to print if there's a missing value in that particular column. So that's what this cell is trying to do. Cool. So fill in the line below how many rows in the trained data. So that is the first value in this tuple, 1168. Cool. Number of columns with missing values. So as you can see here, we have 3. So the answer is 3. Fill in the line below how many missing entries are contained in all. How many missing entries? So I guess we just sum these 3 values up, right? I think that's it. 212 plus 6 plus 58. I think that's pretty much it. All right. Moving on to part B, considering your answers above, what do you think is likely the best approach to dealing with the missing values? Well, judging from this, I think we can probably get away with just dropping the rows entirely because there's only like a few missing values. So we have like 58 rows, 6 rows here out of like 1,000. It's probably, yeah, I guess it's worth it if we just like drop these 2 the rows in these 2, the rows that have missing values in these 2 columns. And as for this, because it's a lot bigger, so we have more missing values in this particular feature, maybe it's worth to, I guess, impute them for lot frontage, and then yeah, and as for these 2, we just drop the rows. Let's just have a look at the solution and see what they say. Run this code to receive credit. Since there are relatively few missing entries in the data, we can expect that dropping columns is unlikely to yield good results, and that is because we'll be throwing away a lot of valuable data. So imputation will likely to perform better. Cool. So let's move on to the next cell. So here we are creating a function called score dataset, which returns the mean absolute error between predictions and the between all the predictions and the actual target in the validation set. Fill in the line below, get names of the columns with missing. I'm just going to copy this and just replace all of this. I think that's pretty much the same, right? So we can just copy, yeah, just save some typing. I'm just going to copy the code. So what we're doing here is we're just looping through each column in the training set. And if there's missing values in that particular column, we want to put it into a list called columns with missing. As for this, we want to just drop those columns with missing values from the training set, and we want to do the same with the test set. and x is equals to 1 here. I think I've explained this in a couple of videos before. So x is equal to 1 means we're dropping vertically. X is equal to 0 means we're dropping horizontally, which is by rows. So let me just go ahead and change this to x test because we're x valid, not x test, x valid, because we're dropping from the validation set. Cool. Let's just go ahead and check our answer. Beautiful. And then we would want to go ahead and apply the score dataset function and calculate the mean absolute error. All right, cool. So this is the mean absolute error if we drop the columns. So 17,837. We want to look at a different approach. So now if we have a look at imputation and compare if it actually performs better. Yeah, I'm just going to copy all this. Paste them. Xtrain columns. So I want to change this to valid. So another thing to pay attention to is look at, if you pay attention to this, so for training set, we're using fit transform, whereas for valid, we are doing transform. So the reason why we do this is because we're trying to prevent leakage. Maybe I'll touch upon the explanation a little bit. So the reason why these two are different is because for Xtrain, we want to fit the imputer to the training set, and then we want to transform the training set. Whereas for validation set, we don't want to fit because we've already fit it to our training set. Because validation set, the whole point of validation set is supposed to be independent, meaning it should not be contaminated with information that is on the training set. Cool. Let's just go ahead and run the cell. Correct. So here we have the MAE of 18,000, whereas for this one is 17,000. So the mean absolute error for imputation is greater than if we drop the columns, which is weird. Compare the MAE from each approach. Does anything surprise you about the results? Why do you think one approach performed better than the other? The reason that they gave here is that simple imputer might not be the best way to impute because there might be a lot of like noise in the data. So if we just, it's a sort of a naive approach if we just like fill the missing values in the column with the average. Here they also mentioned the garage year built column. It is likely that in some cases a missing value can indicate a house does not have a garage. Does it make sense to fill in the median value along each column in this case? Yes. So if a house does not have a garage, it naturally does not have a information for each garage year built. And so therefore, if we just force or try to substitute those missing values in that particular column, we are sort of altering the data in such a way that it's not reflective, it's not true. And so therefore, it might just produce predictions that are not accurate. So here you're just supposed to pick like a, I guess, a method that you're happy with. So here they use median imputation. So I'm just going to copy what they do because I'm trying to avoid spending too much time and making this video too long. So let me just go ahead and copy and paste. And then this is just xtrain columns. Xtrain.columns. We're collecting all the column names, and this is just xvalid columns. Xvalid.columns. All right, let's just run the cell. We want to do dot columns. Dot columns. Cool. All right, moving on. We want to define and fit the model. So this time we're using the median. As we can see here, this performs slightly better than just using mean imputation. All right, cool. Part B, use an Excel to pre-process your test data that agrees with how you pre-process the training and validation. All right, cool. So we just want to use the same method as we did. So with the median imputation, let me just scroll up. So we want to do final imputer transform. Final imputer transform. So pandas data frame. I want to store everything to a data frame. final imputer.transform x test, I think. And then we want to get the test predictions. How do you get test predictions? Press test. So model.predict. We just want to pass in this into here. I think that should work. All right, beautiful. And then we want to save the test predictions and then submit. All right, cool. You can do like this final step yourself, because this is just saving the data frame into a CSV file and then submitting your results, and you can compare the results. For now, I'm going to move on to lesson number 3, which is our last lesson for today. All right, so categorical variable. So in data science, there are 2 types of variables. So there are numerical variables or categorical variables. So numerical variables, as the name suggests, contains numbers. So for example, height is a numerical variable, income is a numerical variable, house prices is a numerical variable. So these are all continuous, whereas categorical variable, on the other hand, are categories. Or are in discrete form. So for example, blood type is a categorical variable. Car brands is another example. So the reason why we need to distinguish and contrast the types of variable is because the way we would deal with them is different. Like for example, the way we would fill missing values are different. The way we would do exploratory data analysis is different. So it's important that we distinguish and we know the differences between these 2 types of variables. So here we're introduced to categorical variable, which takes only a limited number of values. So say for example, here they give 2 examples here. So consider a survey that asks you how often you eat breakfast and provides 4 options: never, rarely, most days, or every day. So these are our 4 categories. Let's look at the next example. So here we have what sort of brand, what brand of car they own. So we have Honda, Toyota, Ford, so these are all categorical. The easiest way to dealing with categorical variables is simply remove them. This approach will only work well if the columns do not contain useful information. All right, so second thing that we can do with a categorical variable is called ordinal encoding. So what encoding is generally speaking, is turning a text variable in a numerical variable. Because machine learning models can't work with text, we need some way to turn these texts into numbers. So this is an example of a type of encoding called ordinal encoding. So what ordinal variables is they are categorical variables, but in a sense they are in order. If a person doesn't have breakfast, it'll get the value of 0. Rarely is next in that order, so we'll get a 1. Most days is next in that order and we get 2. Every day you'll get a 3, and so on and so forth. Yeah, so that's what ordinal encoding is. Let's just move on to look at the third thing that we can do with categorical variables, which is called one-hot encoding. So one-hot encoding is another type of encoding, but the difference with one-hot encoding is instead of having the same number of columns after we perform the encoding, we'll have multiple columns. So here we can see red is turned into a value of 1 in the red column and then 0 for the other colors. Yellow will have 1 in the yellow column and 0 for the other colors. And the reason why we need to make this distinction is because we want to allow our models to realize that a particular column has an order sequence to it. So here, if we scroll back up to the ordinal encoding example, and if we use one-hot encoding in this particular scenario, the model will not be able to recognize that every day is more frequent than most days is more frequent than rarely. We'll just have 1 and 0s everywhere. But because we want our model to recognize that this particular column is actually in order. So that's the reason why we need to make this distinction. Another shameless plug, I wrote an article on the whole topic of encoding and how you can do it in Scikit-learn. I'll also put a link in the video description if you want more information. If you're interested to learn more, I explain in more detail in that article the difference between ordinal variables and nominal variables. So yeah, so make sure you check that article out. I'll put a link in the video description. All right, cool. So now we're gonna, as similar to the previous lesson, we're gonna look at some examples to just solidify our understanding. So here we're doing train test split, reading the data, we're getting our predictors, our target. We're doing train test split. We are dropping the columns with missing values, So yeah, so you can go through all this in your own time. I think we've already covered this in a previous lesson. The first 5 rows of our training set looks like this. So here we're introduced to a new function called dtype, which enables us to check the data type of a column. So here, if we have a look at the, so here we're filtering the training set to only get the variables that have the data type of an object, which is categorical variable. Here we are looking at approach 1, dropping categorical variables, calculating the mean absolute error. I won't go through all this because this is pretty similar. This one is approach 2. So here we are introduced to a new function called ordinal encoder, which is in the pre-processing module in scikit-learn. We want to ordinal encode all the categorical variables. So object calls, I believe, are the categorical variables. Yeah, so we've saved all the categorical variables into this particular variable called object calls. And then we just want to, ordinal encode them. And then once we do that, we can predict and get the MAE, which is 165, which I think is better than approach 1. It's lower. Let's look at one-hot encoding. One-hot encoder is another function in pre-processing as well. We can go through all of this, and then we get a greater MAE. In this case, dropping the categorical columns perform the worst since they have the highest MAE score. As for the other 2 approaches, since the return MAE scores are so close in value, there doesn't appear to have any meaningful benefits over one over the other. In general, one-hot encoding will perform best, and dropping the categorical variables in approach 1 typically performs the worst, but it varies on a case-by-case basis. Yes, cool. So that pretty much wraps lesson number 3. Let's move on to the exercise for lesson number 3. I think that's ready. Let's look at the first 5 rows of the training set. Cool. And here we're defining a function to calculate the mean absolute error between predictions and target in validation set. And here we want to drop columns with categorical data. Cool. So I'm just going to go ahead and copy the code in the lesson. So this is for the training set, and this is for the validation set. So I'm just going to change the xtrain to xvalid, and that should be it. So here we are keeping the columns that are not object, and we're putting into these 2 variables called drop xtrain for training set and drop xvalid for validation set. Cool. And this next cell helps us calculate the MAE, the mean absolute error, which in this case is 17,837. Before jumping into ordinal encoding, we will investigate the dataset. Specifically, we'll look at condition 2 column. The code cell below prints the unique entries in both the training and validation set. So here we're looking at the unique values that exist in the condition 2 feature. So here we have 5 unique values in the training set. Sorry, 6 values in the training set and 6 values in the validation set. I'm not too sure what those values mean, but that's okay. Let's just move on. If you now write code to fit an ordinal encoder to the training data and use it to transform both the training and validation data, you'll get an error. Why do you think we'll get the error? Is it because the values are different? I'm looking at this value here, and there isn't a value in the validation set. So their unique values are different in the 2 data set. That's my guess. I might be wrong, but that's okay. Let's just have a look at the answer. Yeah, so it is correct. Notice that the condition 2 column in the validation data contains the values RRAN and RNN, but these don't appear in the training data. So if we try to if we try to use an ordinal encoding with scikit-learn, the code will throw an error. Yeah, so ideally you'll want to have the same unique values in both the training set as well as the validation set. So that's what they're trying to say here, but that's okay. Let's just move on. This is a common problem that you'll encounter with real-world data, and there are many approaches to fixing this particular issue. For example, you can write a custom ordinal encoder to deal with new categories. The simplest approach, however, is to drop the problematic categorical columns. Yeah, so I'm just going to trust that all of this works. I'm just going to run the cell and all the dysfunctional, problematic categorical columns that have been dropped for us. So now we can now proceed with ordinal encoder. So here we want to drop all the bad label columns, and we want to apply ordinal encoder. So let me just go back and have a look at this, and yeah, just go ahead and copy all of this. This should work now. Cool. Print the MAE. 17,000. Is it better than part A? Is it? Yeah, it is better than approach number 1. Cool. So let's look at step number 3, which is where we are investigating cardinality. We refer to the number of unique entries of a categorical variable as the cardinality of that categorical variable. For instance, street variable has a cardinality of 2 because there are 2 unique values. So the number of unique values for a categorical variable is called cardinality. I'm not too sure how they got the answer though, if I'm gonna be very honest. Let me just replace all of this with 25. Yeah, I'm just being mindful of time because this video is turning out very long. Just going to skip past all this as soon as I can. Part B, for large datasets with many rows, one-hot encoding can greatly expand the size of dataset. For this reason, we typically will only one-hot encode columns with relatively low cardinality. As an example, consider a dataset with 1,000 rows and containing one categorical variable with 100 entries. If this column is replaced with the corresponding one-hot encoding, how many entries are added to the dataset? If we replace the column with the ordinal encoding, how many entries are added? Yeah, so this will be at 99 times 10,000, pretty sure. Yeah, because we have 99 new columns that have 10,000 rows. Whereas this one, we're just converting that existing column that we have to, instead of containing text values, we want to change it so that they contain numerical values. All right, cool. Just gonna go ahead and run this. All right, so one-hot encoding. Again, I'm gonna be really lazy here and just look at the solution. Forgive me guys, because I want to keep these videos short. Cool, and then calculate the mean absolute error. Cool. Generate test predictions and submit your results. All right, cool. That pretty much wraps up what day is it? Day 12. Subscribe to my channel, drop a like on this video, and I'll see you tomorrow in my next video where we cover day 13 of the 30 Days of ML Challenge by Kaggle. All right, peace.